So we're still okay with the second paragraph. All right. So you got 42 to begin with. You pick five of those for testing. All five, passed the test, and then the test engineer told shipping, go like, "Yep, this whole box is ready to go. Okay, it's ready to ship, and send it to our customers." The last paragraph is where the question is. What are the chances that out of the batch of 42 Furbies, where 5 Furbies were sampled and they all passed the quality control test, at least 2 Furbies out of the entire batch were faulty if they had been tested? For this answer, you're expected to compute an actual numerical value while meeting the expectations as outlined in the exam instructions, which is basically asking you to explain your reasoning and do your derivation step by step. All right. So, how would you approach this? So, the first thing is you need to take an inventory of what we have learned in this class, particularly things that we have learned about probability and counting. Okay? All right, so now the next question is to focus on what the question is really asking, which is the last paragraph. What are the chances, which means we're looking for a probability, and when you're looking for a probability, you are looking at the cardinality of the event, which is a set of outcomes that we're interested in, which in this case would be all the outcomes of at least 2 Furbies out of the entire batch are faulty. So you have 2, 3, 4, 5, and all the way up to how many? What is the maximum number of Furbies that can be tested faulty if they were to be tested? We have 42 to begin with.
37.
It'll be 37, exactly, because out of the 42, 5 are confirmed to be good already. So you can only range, so this is ranging from 2 all the way up to 37. For this answer, you are expected to compute the actual numerical value. Okay. All right, so where do we go from here? So in other words, exactly what problem is this? What kind of problem are we talking about here? I sent out 2 documents. The first one I sent was actually the answer. That was actually the solution. So this is the question corresponding to the solution. There are 2 ways to look at this. I mean, the first way is to say, of the 42 Furbies, um, what are the chances that I just pick the 5, or at least how do I pick 5 Furbies out of 42 and they turn out all to be functional? They all turn out to be passing the QC test. But I'm not giving you the actual probability of what are the chances that a Furby is actually going to pass the QC. That's what we're trying to figure out. Is part of what we're trying to figure out is at least 2 of the Furbies were faulty if they were to be tested. So one way to look at this is to go like, well, how about we reverse the problem? How about we change the question just a little bit, and we are looking for the chances of out of the batch of 42 Furbies, only 1 is faulty if it wants to be tested. So the rest are all good. Because it's easier to figure that out compared to, oh, okay, here's the probability of 2 are faulty, here's the probability of 3 being faulty, here's the probability of 4 being faulty, and so on. So we want to just kind of reverse the problem and ask, what are the chances of none or 1 of the Furbies out of the entire batch would be faulty if they were to be tested? Is that okay? So you're only given the fact that 5 out of the 42 that are tested pass the test. So I think in the exam, I was there are 2 interpretations of this question. One interpretation requires that I give people the probability of of what are the chances that if you look at just one single Furby, historically speaking, what are the probability that it it will be passing the QC test. So that'll be the easy one. So let's go ahead and use and take a look at that one first, because the other way, there's actually a way to solve the problem too, but it's a little bit more involved. So I think in the class during the exam, I basically added one additional statement of assuming p is the probability of a single Furby being able to pass the QC test. So given that is what you're given, what do you think is the probability distribution, or what method relates to this question? So think about the testing, or think about each Furby as a ticket. Yes, but I'm looking for the technical term because we have an experiment, we have trials. So each Furby is a single trial. And out of each single trial, we have two possible outcomes, which is passing the test or not passing the test. Okay? But the next Furby is going to have the same two possible outcomes, right? The next Furby is going to have the same possible outcomes, and so on. So what type of problem are we looking at?
Coin toss.
Sorry?
A coin toss.
A coin toss. Okay, very, very good. Okay, so this is parallel to a coin toss problem, which is technically, how do we call that distribution? Starts with a B.
Binomial.
The binomial distribution. Very good. Okay. So if we look at this from the perspective of a binomial distribution, it would be pretty easy to solve. Okay. So let me go ahead and show you um, this thing here, and I need to switch to that. And let me see if I can. It still works. Yep, still works. So I'm going to add a page after. Okay, there we go. All right, so what are we looking at? We're looking at P being the probability of a Furby passing the QC test. So this was added, to the question, during the exam. So given this is the case, what are we looking at? So we are looking at the probability of having 0 or 1 out of 42 Furbies not passing the QC test. Because 1 minus this would be the answer that we're looking for, more or less. But we'll try to figure this out first. So based on binomial distribution, how do we do this? Actually, I make a correction because we really only have 37 left. Because 5 are confirmed good already, right? So you already have 5 out of the box. Those 5 are already good. Of the remaining 37, I want 0 or 1 of those remaining 37 to not pass the test. And P is the probability of passing the test. So how do we formulate this binomial distribution problem? So first question is, what is binomial distribution? What does it look like? What is its state? All right. If this is open book and open test, do you know where to find the material? Okay. So can someone recall what it looks like? I think it starts with a sigma. And I goes from 0 to n. So in this case, n is going to be 37 because we are looking at 37 trials. And then what does it look like? What else is in the sigma? So when you add up all the sigma, it is 1 because when you add up the probability of each one, they all have to add up to 1 because eventually, we want to account for all the different things that can happen. So each item that we are summing is basically asking what is the probability of this many passing the test and this many not passing the test. Do you guys vaguely remember that? Okay. So we're going to use I to represent how many are passing the test, and use n. So n minus I would be representing how many are not passing the test. So we know that p is important because p to the power of I is going to represent the um, the probability of I of the n items passing the test. But what about the n minus I items? Well, those would be the ones not passing the test. So we have 1 minus p that are not passing the test, and that will be raised to the power of n minus I. Are you still vaguely remembering this? Okay, I hope so, because this is something that is in the binomial distribution. So what I'm leaving the space here because the number of these things, how many of these things that can happen, is the coefficient. So in the case of coin toss, okay, if I ask out of 3 coin tosses, how many times you can end up with 2 heads and 1 tail? Okay, if that is the question, you can say, we can have head, head, tail. We can have head, tail, head. We can also have tail, head, head. So those are the individual ways in order for us to end up with, the end result of 2 heads and 1 tail. Is that correct? All right. So in this case, we want I passing the test and n minus I not passing the test. And I'm just asking how many ways can we arrange the passing and not passing so that when you add up all the ones passing the test, it will be I. If you add up all the ones not passing the test, it will be n minus I. So what is the coefficient that we need to put here? It has something to do with, okay, so how do we get to the binomial theorem? What was the one uh, thing, okay, because if I mention the term, you guys will remember. So what is the mathematical concept that we needed in order to prove the binomial distribution theorem? Pascal's identity. Yes. Okay, very good. And Pascal's identity has to do with Pascal's triangle. And Pascal's triangle has to do with the coefficients of a binomial, right? So we have x plus y to the power of n. So the question is, how many of x to the power of this and how many and y to the power of that do we end up with? That's what the Pascal triangle is about. Okay. So if you remember Pascal's identity, what does it look like? Or I should just ask, what kind of mathematical concept does Pascal's identity describe? Combination, very good. So what we have here is a combination thing. And choose I is the coefficient. So this is the binomial distribution. So in this case, I don't need everything, right? Because if I just say, give me the sum of all the probability of every single way of ending up with this many passing the test and this many not passing the test, that's not important because we already know what the question is asking is 0 or 1, not passing the test, right? So in this case, it will be 36 passing the test and 37 passing the test. So what we need to, so the actual answer is going to be 37 out of 37 are passing. So you have p to the power of 37. Technically, you should also mention 1 minus p to the power of 0 because that's the counterpart of the ones passing the test. But we also have the other one, which is 36 out of 37 that are passing the test. So in this case, we have 1 that is not passing the test. So when you look at this, the sum of these two terms, that would be the answer. Because we already confirmed 5 out of 42 are passing the test already. So the question is, of the rest of the remaining 37, what are the chances that we pick 37 out of 37 that are all passing the test versus 30, 37, 36 out of 37 that are passing the test? So that's one way to look at this. Okay. The other way to look at this is to let me go back to the question first. So the other way to look at this, where's the question? Right there. Okay. So the other way to look at the question is you let's say you do not know p. Okay, so that's an unknown. Can we still solve the problem? That's the question. Can we still solve this problem without knowing that p to begin with? So let's read the question again. What are the chances that out of the batch of 42 Furbies, where 5 Furbies were sampled and passed to QC, at least 2 Furbies out of the entire batch were faulty if they had been tested? So I'll let you guys think about this for a little bit, and then we'll come back to this one. But knowing P to start with is an easy problem because we can just use the binomial distribution and solve this problem. So I can give you a hint of what tool you need to solve this problem. It's going to be counting. Okay, so counting is the other way to solve this problem. All right, so question number 2 has to do with the graph algorithms. So it's either A star or Dijkstra's algorithm. So we'll take a look at the question. You are given a graph G equals to VE, where V, the set of all the vertices, would be K, M, N, M, J, A, R, Q, P. So they look kind of random because I want to avoid the use of the letter D for distance and some of the other letters that are also used in the algorithm itself. E is BA, MQ, MB, blah, blah, blah. The H distance function is this. So I'm representing everything in the form of a set. The set of destination vertices is R and J. So as soon as you know the set of destinations, which algorithm do you think this question is about? Well, we only have 2 algorithms, right? We have A star and then we have Dijkstra's algorithm. Which one takes on a set of destinations? Because one of them can only handle one destination, the other one can handle multiple destinations. So the one who can handle multiple destinations is Dijkstra's algorithm. Exactly. Okay. So we kind of know that this is about Dijkstra's algorithm, but the next sentence confirms that. But the way I describe this is to see if you understand each algorithm. Okay. If I'm giving you a set of destinations, that by itself is a strong indication that we are dealing with Dijkstra's algorithm. So apply Dijkstra's algorithm to produce a trace of how variables are changed during the execution of the algorithm, as discussed in class, in homework, and also in the module. In other words, this is basically a repetition of your homework assignment, given a slightly bigger problem because this graph is a little bit more complex. And then the next paragraph says your trace should show that you know how to follow the algorithm and perform all the steps. This means all updates should be shown in the correct order of rows. And in this case, I think I also supplied a table to the class. To balance details with the length of the trace, you can collapse certain sequential steps to a single row, but only to the extent of the solutions of the homework and example traces as discussed in lecture. So basically using the same format as in the homework assignment. Do not work on the trace using an app outside of Google Doc, which I'm not concerned about because this entire exam is on paper. There's a link to the template. Okay, so I can open up the template so you know what the template looks like. So this is basically pre-formatted. I will give you at least something comparable to this. So this way you don't have to bring a ruler and try to align your own stuff. Okay. So this is already given to you, and we just want to fill in all the cells to represent the execution of the algorithm. So let me finish reading the whole thing. Your trace is expected to be consistent with text solution to the assignment and text demonstration when the assignment was released. You can include additional comments and explanations in your trace, but your trace should not include any less information about how the algorithm works. Okay, so do you guys want me to solve this, or do you think, oh, this is the same thing as the homework assignment? I got that already. You want me to solve it? Okay.
Yeah.
All right, cool. So we'll go ahead and make a copy first because I don't want to mess up this one. So we'll go ahead and make a copy. And since it's in my own folder, I can create it anywhere. All right, so here is the trace, and I want to peel this out so I can display both the algorithm, I mean the assumptions and the trace at the same time. All right, so maybe I just need to resize it manually and then peel that out like so. And then we overlay this on top of the problem, which is here. There we go. Um, I probably want to make this all the way here. So this way I have more area for the trace. Ah, okay. I think that's good. All right. So now you have to remember how the whole thing is initialized. Um, I have the algorithm memorized because I wrote the module and stuff. So I already know that I have to initialize all the L values. And do you remember what each L value is representing? L stands for length, right? So it's the length of what?
Node to a destination.
The length of the shortest known path up to this point to a destination. Yep. Okay. So that means anything that is a destination is going to have an L value of 0 because we're already at a destination. And then for the rest, it's going to be infinity because we have not yet identified a path at this point, okay? Because we are simply initializing at this point. So that means, okay, so let me see if I can do this. Okay, I'm going to make this a little bit smaller so I can overlay and make a better use of the screen space that I have. Okay, that works better. All right, so we know the destinations are R, N, and J. So that means L of R is going to initialize to 0. L of N is also initialized to 0. R of J is also initialized to 0. Everything else would be infinity. So you just, I mean, if you're writing, you can just use the infinity symbol, like so. Okay, not too hard. And we also know that E prime is initialized to E prime would be the set of all the solution edges. And since we're at the beginning of the entire algorithm, so how should E prime be initialized? Empty. Very good. And then Q is our starting point. Okay, the initial point, the initial value of Q is the starting point. And this is where you want to remember the direction of expansion of Dijkstra's algorithm, at least in this class, is opposite to the direction of expansion of the A star algorithm. So what do you think Q is going to start with? I mean, the other algorithm starts with a start vertex, right? This one does not even tell you what is a start vertex. So you have no choice but to start with the destinations. Yep. So Q initially would be identical to the set of all the destinations. So we have R, N, and J in it. So so row 2 of the spreadsheet is representing the after initialization. That's what we have. And you can collapse all those rows into one single row, just so that you don't end up with a lot of different rows. Okay, so now we're ready to get into the loop. The loop of Dijkstra's algorithm is only checking whether Q is empty or not. As long as Q is not empty, we're not done yet. So Q is definitely not empty. When we get into Dijkstra's algorithm, the first thing we do is we say, well, let's pick a vertex V, okay, or let's select one of the vertices from Q and use V as a variable to store that particular vertex. The criteria is we have to find one that has the least L value because it's a quote unquote greedy algorithm, which I would probably describe as optimistic algorithm. And at this point, all of those vertices have the same L value, so it doesn't really matter which one you choose. So we'll just go ahead and choose R first, and then you have to take it out of Q. So Q now only has N and J in it. And now we have to look into all of the incoming edges that end with R as a vertex. So we are looking at edges where R is the second tuple or second item of a tuple instead of the first item of a tuple. So you look at the edges or the edges described here, but you can also look at the distance because the distances also have the same number. They all have the same edges. So you can also look at the set D, which is the set of the distances. So we're looking for things that end up with R. So A goes to R. That's one. Yeah, that's the only one. So that means we only got one edge to talk about here, which is from A to R. And now you have to remember in the algorithm, we have to, there's a comparison. And the comparison is looking at the distance from W to V and then add L of V to that distance. And then we ask whether that is less than L of W or not. So we look up L of W. L of W is L of A, it is infinity, and we look at the distance from A to R, it is 2, and then we look at L of R, which is 0. So we have 0 plus 2, which is 2. That is representing a length of an alternate path from vertex A to a destination. So we compare that to the length of the quote unquote shortest known path up to this point from vertex A to a destination, which is infinity, which means I have not found a path yet at this point. So that means, did I find a shorter path? Yep. So we have to do some updates. So the updates would include updating L of A to be 2 in this case. We have to update E prime to include this edge, which is from A to R. And we also have to remember to add A to Q. So Q now has N, J, and also A in it. Is that okay? I mean, you guys can look up the algorithm and follow along, but I think I got the algorithm memorized. So that's one edge, and I think that's the only edge from A to R. And let me just kind of do a quick run here. Yep, so that's the only one. So we are now done with the for each loop, and then we get back up to the while loop. So the while loop is looking at Q and ask, is it empty? Nope, Q is not empty. And now we have to pick one vertex out of Q that has the least L value. So we got N, J, and A. N and J are both destinations, so they both have an L value of 0. So I can pick either one because they're the same. So let's just say that I pick N this time, and that means I can no longer have I can no longer have N in the set of Q, and now I have to look into all the edges going from some other vertex to vertex N. So looking at the description of E, K goes to N, and that's the only edge. Okay, so we know that Kn is the only edge ending up at vertex N. And we look up, L of K, it's currently infinity, which means we're guaranteed to have found a shorter path. So we now look at the distance that ends with from K to N. So K to N has a distance of 2.5. 2.5 plus 0, which is the L value of N to begin with, is also just 2.5. So that becomes the new value of L of K, which is 2.5 here. And we also now have to add a new edge. And this is from K to N. And we also have to remember to add K to the set. There we go. Oh, we have to add k, not n. Sorry. Let me fix that. Like that. Okay. That's the only edge. Okay, this is the only edge ending up at vertex n. So we are now concluding with the for each loop. We go back up to the while loop. We look at the set cube, definitely not empty. And now we have to find the vertex in Q that has the lowest L value. Now that's going to be J, because L of J is 0. The other two are non-zero. Okay, so we have to look at, we have to pick J out of the entire set. So this is now J, and then we take J out of the set Q. Now we have to look into all the incoming edges that end up at vertex J. So looking at the description of the edges, we have PJ is the only one. So that's the only edge we have to worry about. So we will basically represent that. So P is here. And the question is, did I just find a shorter path from vertex P to a destination? The answer is yep, because L of P at this point is infinity. Oops, so I just pressed the wrong key. There we go. So the question is, okay, I just found a shorter path. What is the length of the shorter path? L of J is 0, which means it's a destination. The edge PJ has a length of 6. Okay, so I just found a path with a distance with a length of 6 from vertex P to a destination. So this gets updated to 6. And then we have to add that edge to the set. So we have AR, KN, and now we have PJ. But we also have to remember to add P to the set Q. So set Q now has A, K, and P in it. Are we still doing okay so far? So you can see how I'm doing this without using a visualization of the graph, because that really is not necessary. I mean, having the graph being visual may help, but I don't think it's going to help that much, okay? Because you still have to kind of go through the algorithm, find the least L value, and so on. So now that we have A, K, and P in the set Q, once again, we have to find the one with the least L value. The one that has the least value is A, because it has an L value of 2, as opposed to 2.5 and 6. So this is going to be the next vertex that we choose. So we have A chosen here, and A is no longer being in the set. So now we have to look into all the edges that end up at vertex A. So we got BA, okay, that's one edge, and that's all we have. Okay, so this is B, and because B still has an L value of infinity, I'm pretty sure we just found the shorter path. So the shorter path is going to be the L value of A, which is 2, added to the distance from B to A. So according to this, going from B to A has a distance of 9. 9 plus 2 is 11. So that means the new L value of B is going to be 11. And then we have to add that particular edge to the set. KN, PJ, and now we have BA. And then we also have to add B to the set, KPB, like so. So do we have any other edges ending up at vertex A? Doesn't look like that, okay? That's the only edge. So now we're back to the while loop again. So in the while loop, we are looking at the 3 vertices in Q, and then we ask which one has the least L value at this point. L of K is 2.5, and I think that's the shortest one. So we have to choose K in this case, because it has the least L value. So now it is no longer in the set Q. And then we have to look into all the incoming edges to vertex K. So according to the description, Q goes to K, and that's the only edge going to vertex K, and that has a distance of 2.5. All right. So we now look at Q to K. Let me double check. Yep, QK. And L of Q is still infinity. That means we are guaranteed to have found a shorter path in this case because any real value is going to be less than infinity. All right, but the question is, what is it? So if we look at L of K is 2.5, and then the edge from Q to K is also 2.5. So that means I have found a path with a length of 5, which is 2.5 plus 2.5, from vertex Q to a destination. So we update the L value to 5, and then we have to add that edge into the set. So we got AR, KN, PJ, BA, and now we have QK in E prime. And then over here, we have to remember to add Q to the set. So we have P, B, Q in the set uppercase Q. And that's the only edge we have. So that's the end of this for each loop. We go back to the while loop. We look at P, B, and Q, and then find out which one has the least L value. All right, so P has an L value of 6, B has an L value of 11, Q has an L value of 5, so we're going to pick Q this time. Oops, I keep pressing the wrong key. So this is Q, and it is now taken out of the set. So we only got P and B in the set here. And now we have to look at all the edges that end up at vertex Q. So let's take a look. MQ, that's the only one. So we only got one edge to look at. Vertex M still has an L value of infinity, so now it has to be updated. L of Q is 5, and then the edge MQ has a distance of 9, so 9 plus 5 is 14. So we update this to be 14, and then we also have to add the edge. So yes, I know you guys cannot do this when you're in a paper test. So that's why I have to keep in mind not to make it, not to make sure it's not involving too much writing. So we got MQ in here, but we also have to add M to the set, PBM in this case. Now we're back to the while loop. Out of the 3 vertices, we have to pick the one with the least L value. So P has an L value of 6, B has an L value of 11, and then M has an L value of 14. So P is the one with the least L value. So we're going to pick P as our next vertex to quote unquote expand. And now we have to look at all the vertices or all the edges ending up at vertex P. So let me take a look. MP is the only one. All right. So this is M here. And if you look at M, it already has a L value that is not infinity. So this time it gets a little bit tricky because now we actually have to do the comparison and see whether we have found a shorter path. So the length of the path that we have just discovered has a length that is based on L of P. L of P is 6, and then we have to add the distance from M to P. And to go from M to P is 2. So 2 plus 6 is 8. 8 is less than 14, so we did find a shorter path. So we have to update this. But this time it is a little bit trickier because we have to look at E prime and we have to take out the one edge going from M to something because what we have discovered is there's a shorter path from M to a destination. So that means we have to remember to take out MQ, or if you want to, you can just substitute this Q with an M. But we do not end up with MQ and MP at the same time in E prime. We have to take out the one that existed before starting from M to somewhere and then replace that with the new edge. So it also means that we have to put M back into the set, but it really doesn't do anything because M is in the set already. And I forgot to do one thing. I forgot to take P out of Q. So this is really just B, M over here, and the same thing over here is we only have B and M in the set at this point. Are we still doing okay? If this is really boring at this point, it's a good sign because it means you guys are really understanding the algorithm, or not understanding anything at all, because both will contribute to the feeling of boring. So I hope it is the former, where you go like, yeah, I know how it works, okay? So, but I'm gonna finish it anyway because we are already close to the finish line. So now we only have B and M left. B has a L value of, okay, let's just scroll up the screen at this point. All right, so I'm gonna have to do this trick here because at least I need to know, the column header. So B has an L value of 11, and then M has an L value of 8. So M is the one that has a lesser value. So we choose M and then take it out of the set. And now we have to look at all the edges ending up at vertex M. Nothing. Okay, there are no edges ending at vertex M. So we are done with this particular iteration of the while loop. To get back to the beginning of the while loop, we have one vertex left in Q. That has to be the one to be chosen. So B is chosen because it's the only thing left. And then we are asking, what edges would go to vertex B. So as far as I can tell, nothing. So there are no edges ending up at vertex B. So as a result, we're done.
There's MB.
Oh, there's MB? Oh, okay. Thank you. So there's MB. And now we have to look at the edge MB and ask, did I just find a shorter path for M? Okay, so we have to compare to 8 at this point. L of B is 11, and then the edge MB has a distance of 9. 9 plus 11 is 20. We are not finding a shorter path, so there's nothing to update, and as a result, we are not adding anything back to Q. So by the time we get to the while loop, Q is now empty, the loop is done, and this is all finished. So are we good so far? All right. So that question number 2, which is really kind of mechanical, if you could finish the homework assignment without any problems, you should be able to do this without any problems. It's open book, open notes. Okay, so I strongly suggest you to bring along your printouts of the algorithms, so that this way you're not relying on your own memory of how to run the algorithm. Are we good so far with number 2? Okay, moving on to question number 3. So here's question number 3. Question number 3 is also fun. This is one of those probability ones. A grower has 60 spots to grow a crop at the beginning of a growing season. The per seed germination rate is known to be 0.82. So that means if you look at each seed, the chances of the seed germinating is 82%. Is that okay? All right. The grower guesstimates that a buffer of 10 seeds should be enough. So this means we now have 70 seeds are going to be, will attempt to germinate 70 seeds, hoping that at least 60 of those would germinate successfully, so that we will have those available for the growing season. So let me just check to see if the question itself is understood at this point. Okay, so I have a nursery. We have 60 spots, and I want to have at least 60 seed that germinates successfully in order to use all 60 spots. But the chances of each seed germinating successfully is only 82%. So you are hired as a consultant to help the grower to optimize the number of seeds to germinate. In other words, you're trying to figure out, okay, is 10 a good buffer, or can we reduce it, or do we need to increase it? Compute the probability that the grower will indeed have at least 60 seedlings. In other words, you do end up with at least 60 seeds successfully germinating. For this answer, you're explicitly required to use the sigma notation to express the probability. No actual numerical value is expected. Otherwise, the instruction of the exam is applicable, which means you have to explain to me why you think this is a blah, blah, blah distribution and why you apply this equation and so on. Yep.
AI solves this question perfectly. Like, it gives you the exact same answer that you had on here.
Wow. Well, one more reason to conduct all the exams in person and on paper. But it also, kind of adds. I think it will add. It should add to your anxiety of if the AI can do this and the AI can write program to solve your lead code problems already. How do you convince a potential employer to hire you? I hear silence, right? Complete silence here. It's like, hmm.
Make the AI.
Hmm?
Make the AI.
Make the AI? Well, the AI is already here. Open AI is already here and it's free.
Make a better open AI.
So, but to do that, all you have to do is to ask OpenAI, how do we improve you? And it will probably write an essay, 1,200 words, outlining exactly how to do that. I mean, if it could, that would be creepy. Because then we become a component of the AI system instead of the other way around. We become the tool of the AI system of saying, well, certain things can only be done organically, and you are a component to help me do that. So the AI becomes the overlord. I think this is something that some of you will probably have to deal with, okay? Because this is what AI can do at this point, is to look at one of the questions in tax or final exam, which is, I have to add, it is not known to be easy. My final exams are not known to be easy. So the AI not only was able to understand the question itself, so no one can now say, Tag, I think the way you asked the question is not very clear, because obviously the AI disagrees. The AI says, yep, it's clear enough, I can figure out the answer.
It didn't get 1 in 4.
Hmm?
It didn't get 1 in 4.
It did not get 1 in 4. So it would still pass the class.
Yeah, with a 50%.
I think that is creepy already. And due to Moore's law, which basically is sort of equivalent to doubling the performance of system every 18 months. So by the time you graduate with a bachelor's degree, it would have doubled already. So not only do you have to think about what it can do today, you also have to kind of think about in 2 years, or by the time you graduate from with a bachelor's degree, what can AI do? So I would kind of keep it in the back burner because I think that can impact what you want to focus on. Okay, what can AI not do? How can you sell? Okay, this is what I can offer you, and this is not something that AI can do at this point. So, just a little segue to depressing news and fact. And it's not depressing only to CIS. I think this is equally, if not more depressing, to English majors or journalism. I mean, because in those fields, I mean, it's even worse because they are not even in a situation where, but I understand how the AI works, right? So I can offer ways to enhance it, or I know what problem I can solve that the AI cannot solve. Because if AI can write all the journalism pieces already, um, you know, you don't need to hire a lot of people to write for newsletters and whatnot. You just have to ask the AI, write a 2,000 word article on whatever topic is hot, in on that particular day. All right. So getting back to here, we'll continue with the question number 3. All right. So how do you solve this problem? So we already know what P is. Okay. First of all, what type of problem are we dealing with here? There are only a few problems that we are dealing with. I would categorize the two main problems to be binomial distribution versus counting. So which one is this? Is this counting or is it binomial distribution?
Binomial.
It's binomial distribution. And what is the signature? What is the telltale sign of you're dealing with a binomial distribution? Let's start with the term binomial. Okay, what is that telling you? You got two, right? BI is two. So you got two what? Two outcomes per trial. That is the key of identifying a binomial distribution. Is you first have to identify what is a trial. What is the experiment? What is a trial? The experiment in this case is you got 70 trials. You got 70 trials because each seed is representing one trial. What outcomes are we talking about? Because whenever you talk about a trial, you have to think about what are the outcomes of a trial. Well, we can either have the seed successfully germinate, one outcome, or not germinate. That's the other outcome. Okay? And every seed can either germinate or not germinate. So that's why we know that this is a binomial distribution problem. Okay, now that we know it's a binomial distribution problem, how do we use the binomial theorem to solve the problem? I basically presented that already earlier. So the question is, how do we solve it? What are we being asked for? So what we are asking is compute the probability that the grower will indeed have at least 60 seedlings. So that means having 60 seedlings germinating is one of the outcomes that we like. 61 is good, 62 is good, 63 is good, all the way up to 70. Because we have 70 seeds to begin with, so having all 70 to germinate successfully also meet the criterion to be counted in the probability. The question clearly asks that you do not give me a specific number and instead using the sigma notation. So what I have described up to this point, those are the things that you need to put into the answer. Okay, why do you think this is a binomial distribution? If it is a binomial distribution, what is the experiment? How many trials do we have in the experiment? And if this is one trial, what are the outcomes of each trial? So those are the things that I need you to be put into the answer, is to explain your reasoning to arrive to the conclusion that we're dealing with a binomial distribution. So did the AI explain that to you?
Yes. Yeah, it's amazing.
Isn't that amazing?
You want me to read the answer?
Sure, go ahead.
To compute the probability that the grower will indeed have at least 60 seedlings, we need to use a binomial distribution formula. This formula is P of x equals k, n choose k, times p to the power of k, times, I could keep reading, but it keeps going like this with the steps, and eventually ends at the sigma notation of 70 choose k times 0.82 to the power of k times 0.18 to the power of 70 minus k for k from 60 to 70, which is the exact answer, which was.
Well, looking at it in a kind of pessimistic way, at least you know tech was not wrong. OpenAI can double check that your professor is not smoking something when he was writing the answer. So that was, I think that's also interesting because yeah, that's interesting. But basically, this is the answer. This is the sigma notation that I'm looking for, where I is representing the number of seedlings that successfully germinate. So it has to range from 60 to 70. And then we have to use 70, choose I, that's the coefficient. And then we have 0.84, which is the chances of successfully germinating to the power of I, because I is representing the number of seed that germinates correctly or successfully. And then 1 minus 0.84, which is 0.16, is the probability of not germinating correctly, and that's raised to the power of 70 minus I, which is representing the number of seeds that did not germinate correctly. All right. So do we have any questions about this? Other than what is the point of classes now? Yes.
Did you get 0.84? It was 82.
Oh, was it 182? Okay, so it was a. So that was my mistake, and I'll just go ahead and fix that. So we're looking for the eraser right here, and we just have to erase the that and that. All right, so there we go. So it will be kind of interesting to see how enrollment changes from here on for computers for CIS classes or for the transfer degree. This has been the most depressing class of the entire semester, right? All right. So moving on to the next question. Nope, not that. Not that either. There we go. All right, so we are moving on to question number 4 out of 4. And okay, that's because my browser is too tall, so I can't see the entire thing. Still too tall. Okay, now it's about right. All right, so this one is also a probability thing, but we'll try to figure out what kind of probability thing it is. So I'm just going to read the question. So Tristana, Ishine, Jane, Lakis, and Athrin are friends in the same class of 26 students. When they arrive at school and line up in a class-specific single file to get ready to enter the classroom. Okay, so let me just pause here. Do you guys understand what I mean by this?
They're
So-
in one line waiting for class.
Right. So single file, which means this is a you can kind of look at it as a singly linked list, right? It's just single file. Um, they prefer to be together. So these are friends and they want to be together so they can chit chat and whatnot. You may assume that the order of arrival of students is random. So we don't know any specific distribution of when which student is going to arrive, because in reality that is not actually random. Okay, but in this case we assume it's just random. What are the chances that these friends are contiguous in the class specific single file? You may assume full attendance. So you may assume that this entire class is always going to be there. So 26 students to the whole class, and then we have 1, 2, 3, 4, 5, and we have 5 people who want to be together when they wait to get into the class.
That's 4 people. 4 people. Oh, no, 5. Yeah, 5.
There are 5. So to think about this question in an easier way, you can think about just students A, B, C, and D. Think about all the ways to end up with A and B being together. So in other words, A, B, C, D, B, A, C, D, D, A, B, C, and D, B, A, C are all satisfying the requirement, but these may not be the only ones. Okay, so in quotes, in parentheses, while A, D, B, C, and B, C, D, A do not. So because in this case, A and B are spaced out by D, and A and B are spaced out by C and D in this case, this may help you formulate your approach. Okay, so what kind of a problem is this? First of all, do you see anything here that might tell you that this is a binomial distribution? Nope. So since it's still asking about the probability, it has got to be the other one, right? So it has to be dependent on counting. What are we counting? So when you have a counting problem, then the next question you have to ask is, are we dealing with something that is without replacement or something that is with replacement? So in this case, it is without replacement. So because you can imagine that you have 26 marbles in a bag, okay, and you're just taking marbles out of the bag and put it into a single line, and you try to ask what are the chances that these 5 specific marbles will be right next to each other in that line. So we know this is without replacement. So if you once you combine this is not binomial distribution, and each trial is without replacement. Whatever is taken out of the bag cannot be considered again in a later trial. Then the next question to ask is it a combination or is it a permutation? Combination means ordering is not important. Permutation means the ordering is indeed important. Okay, so those are the things that should be floating in your mind right now. Okay, those are the questions that you want to be able to answer. So how do we approach this problem? We got 5 people who want to form a group, right? So they want to be together. As long as those 5 people are together, we don't really care about the rest of the class. Okay, the arrival order and whatnot, we don't care. So how do we approach this problem? Since it's asking about the probability and it's not binomial distribution, so that means the only way you can compute the probability is to have the cardinality of the event as the numerator divided by the cardinality of omega. Omega as a set is the set of all possible outcomes, and E, or the set of events, is representing the outcomes that are of interest to us. So now the question is, what does an element look like in E, and what does an element look like in Q? I mean, obviously, everything in E is also in Q, so the question is, what does one element look like in that case? What do you think? Yep.
So the numerator would, you first have to figure out how many different ways those 5 students can be arranged among themselves.
That is a factor, yes.
And then you have to multiply that by the amount of ways those 5 kids could be in a class of 26 people. Is that 26 choose 5?
Mm,
No, I don't
it
know.
would not be 26 choose 5 because 26 choose 5 would give you the number of ways of choosing 5 people out of 26, but we don't want to choose those 5 people. We know exactly who those 5 people are,
Right.
right? So we're not choosing. The 5 are not being chosen.
I don't know what to multiply it by.
Yep. So the way to think about this is so there are 2 factors that are important. The first one is, let's just figure out, assuming the 5 people that are interested to be together are indeed together. How many ways can we arrange the other 21 students? Is that making any sense?
Yeah, and that's kind of like doing the, it's like if you do, well, that's like 20 plus 19 plus 18 plus 17. You're trying to find how many different combinations you can get of the other 21 students. That's how you would get the total number.
There's an easier way to look at this, okay? So instead of looking at those 5 people as actually 5 people, we look at those 5 people as one single unit, okay? So we have, the whole class has 26 students, right? So we have 21 other students plus the group of these 5 students who want to be together. So we have 22 quote unquote things. So now we ask, well, out of 22 things, how many ways can you arrange where ordering is important? So in this case, when we look at the permutations of these 22 things, we are looking at this entire group of 5 people as one single thing. Is that okay? So there are 22 factorial way to arrange 22 items where ordering is important. Okay, so let me write it down first. Okay, so we got 22 factorial ways to arrange 21 other students plus the group. Okay, is that okay? Because so the group itself can be the first of the 22, can be the last of the 22, can be somewhere in the middle, and how the other students arrange is kind of like Okay, that's taken care of all those counting. Is that okay? So of this many ways to arrange, the 5 people in the group, they're being together, and the other students being somewhere else. Okay, it's not taking into consideration that these 5 people within the group can also have 5 factorial ways of arranging their own ordering. Does that make sense? But because we have, okay, let's just call the few people in the group A, B, C, D, E. So within a group, okay, they can be arranged as A, B, C, D, E. They can be arranged as A, B, D, C, E. They can be arranged as E, D, C, B, A, blah, 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 blah. Okay? So we have to remember to multiply that. Okay? So there are 5 factorial ways for the friends to arrange to be ordered within the group. Okay, so let me just check whether that makes sense or not. So the 22 comes from the fact that we have 21 other students other than the 5 that we're interested in. So, but plus the 1, which is the group, the 5 people who are together. But that is not taking into consideration of those 5 within the group. Well, they also got 5 factorial ways to arrange among themselves. Is that okay? So that means this is the cardinality of E is 22 factorial times 5 factorial. Does that make sense? These are all the permutations that would meet the criteria that the 5 friends are together, but the rest of the class, we don't really care. Is that okay? So now the remaining question is, what is the cardinality of omega? What is omega representing? Omega is representing the outcome set of all the different ways to arrange the 26 students with no restrictions whatsoever. Is that okay? And since we are talking about permutation and we are looking at choosing 26 out of the 26 students, but ordering is important. So what is the cardinality of omega in this case? It will be the P2626, which is also just 26 factorial. So this is 26 factorial. So that means the probability that we are looking at is just the ratio between these two, which is basically 22 factorial times 5 factorial divided by 26 factorial. Is that making any sense? All right. So are we kind of getting an understanding of how to look at the problem and figure out what tools relate to a specific question? I mean, the graph problem is easy because that's clearly stated. Use Dijkstra's algorithm to solve this, right? So there's nothing for you to choose in that case. But for the other 3 questions, you kind of have to look at it from the perspective of kind of like a decision tree, okay? And the way I would structure that decision tree, I mean, you can use a different way, is to say binomial distribution versus non-binomial distribution. Because to identify binomial distribution is relatively easy. You have to look at the experiment. The experiment has trials. And then you have to look at each trial and say, what exactly is a trial? And then you ask, how many outcomes do we have from each trial? If the answer is 2, no matter which trial we are talking about, there are 2 outcomes, you're probably looking at a binomial distribution. Not always, but I'm going to say most of the time. That is a telltale sign that you're dealing with a binomial distribution. If that is not the case, okay, then you're looking at a counting problem. So in a counting problem, the probability that you need to figure out is going to be a division where the numerator is the cardinality of an event, which is a set of outcomes, and then the denominator is going to be the cardinality of omega, which is the set of all the possible outcomes. So in that case, you have to ask yourself, um, is it with or without replacement? In other words, once a particular trial has a specific outcome, is that outcome still available for a later trial? If the answer is yes, it is still available, then it is with replacement. If the answer is no, that particular outcome is forever not available for all the later trials, then it is without replacement. If it is without replacement, then you have two choices. Is ordering is important? Am I really just looking at membership? Is this a part of that, which is kind of related to the concept of a list? Excuse me, a set, or am I looking at something where ordering is important? If the answer is ordering is not important, you're probably looking at combination or the number of combinations. If the answer is yes, ordering is important, like in this case, then you're probably looking at permutations. Is that okay? So that's kind of the decision tree in my head that I would be using when I look at these questions. Are there any additional questions about these four? Yep.
Not about the four, but in general, should we expect other topics that we covered, questions on other subjects?
Those are much harder to ask questions with the variations that I put into these questions. So I cannot definitively answer that question right now, but I can say in all the past final exams, I have not found a good way to ask about the other subject that we have covered. So I think you're looking at all the types of questions that I would possibly ask. So okay, so let's go over the other topics, right? So one is predicate calculus, which is kind of Prolog, because I use Prolog as a programming language to explain that. I don't think we got enough exposure or enough time to talk about Prolog, so I don't feel that it is fair to ask questions in the final exam with Prolog. But the funny thing about Prolog is it also relates to OpenAI, because Prolog was the programming language of choice back in the 80s when people wanted to do AI systems. So from that perspective, it does have a strange relevance, especially to the discussion that we talk about today. But in terms of the final exam, it's probably kind of difficult to ask questions with Prolog. I can. It's not like I cannot. It's just that I don't think it's going to be fair because we did not spend a whole lot of time talking about how to program in Prolog. And then the other one that we talked about is time complexity. So time complexity is not something that I can easily generate variations, because I can give you an algorithm and ask what is the time complexity of this algorithm. That's not very variation friendly. Um, and also time complexity is it's really heavy duty math. Okay, there's a lot of math involved in time complexity, and we did not spend enough time to really talk about the math part. So I don't feel comfortable or fair to ask too many ask questions about um, time complexity. But there are variations of ways to ask questions related to the algorithms, like Dijkstra's algorithm. I can give you a partial trace. I can reverse the type of question. So I just want to give you guys an idea of what things are possible. So I can give you something like this, or with certain things this not disclosed. Okay? And I will go back and say, okay, generate the graph for me. Okay, so that's a particular question, the type of question I can ask you. So I can leave some of these items empty and give you this part of the trace, and I would just say, okay, I know I'm not giving you everything, but you can go ahead and just give me the distance function that will make this happen. Make the trace consistent with this order. Is that okay? So that's one thing you can try to do yourself, is really just to say, okay, if the L values here, these are all not given to you, but this part is all given to you. Is there a way for you to find the distances to make it consistent? There's not a single answer, there's a whole bunch of answers that can make this happen. I just need your answer to be consistent with this particular trace here. So you might want to look at it that way because it is at the end of the day, I'm trying to see if you understand the algorithm. Going forward like this is one way to ask the question, but giving you the trace and not show you the L values, how they get updated, and ask you to come up with the distance function. So the trace, the end result is consistent with this trace. That's the other way to ask the question. Is that okay? So just be prepared that there will be variations of the questions compared to what you see today. And what you want to do is to focus on the concept a lot more than the process that I used today to answer the questions. Are we good so far? All right. Now we still have Wednesday. Wednesday is still a lecture day. So if you study and you look back into these content and you look at the questions that we have asked here, you go like, I'm not 100% clear about this. That would be a good question to bring to the class on Wednesday. And you don't have to ask the question in class if you don't feel comfortable. You can always send me an email with a question. Yep.
Oh, can we just restate the date and time of the final?
Yes, I can. In fact, I don't have to. That's something OpenAI probably cannot answer. Unless it has access to the web and can do a Google search, then it might be able to answer the question. It can parse the exam schedule. All right, so let me find the class first. Where? Okay. This is a better tool to search for all the tabs. So I just look for 440. Nope, I don't have it open. How can that be the case? Okay, maybe announcement. I don't have announcement open either. Huh. Okay, well, that's fine. I can just sign in right now. There we go. It is also in the class calendar. So that's what I'm trying to get to. All right. You can ask OpenAI, what is tax password? I mean, that's actually the premise of one of the animes. Summer War, it's about AI, and it was able to hack into some of the key accounts. All right, so if you get to the class page and you go to the calendar, I put the final exam in the calendar already. So for those of you who kind of synchronize your own Google Calendar with the Canvas calendar, it would actually appear on your own calendar automatically. So this is it's going to be on the 14th. I'm pretty sure I specified the from and the to. I think it is from 3 p.m. to 5 p.m. So the final exam is a 2-hour thing. And let me just double check, okay? Because I really want to double check and not make sure I don't give you the wrong time. All right, so generally speaking, unless you have a professor who changes the exam time, with a in-person class, this is how we decide when the final exam is going to be. So in this case, we have a Monday, Wednesday class. The start time of the lecture is at 3 o'clock, which is between 2:45 and 4:25. So the correct time is indeed 3 to 5 p.m. on the 14th. So we have a little more than a week, to prepare for the final exam. No, we do not. So the last day of lecture is this Thursday. Hmm?
Wednesday.
Well, for this class, it is on Wednesday, but assuming some of you have Tuesday, Thursday classes, Thursday is still a day of instruction. and then Friday is technically the beginning of the final week. So we still meet on Wednesday for this class, but we won't have a class next Monday. And then the exam is next Wednesday. Yep.
We want class next month.
No, we don't have class. Yeah,
We do
don't
not.
have class.
Yes, no class next Monday.
So this Wednesday is not
Sorry?
this Wednesday is not the final.
This Wednesday is not the final. It is next Wednesday, on the 14th. On the 14th.
The 14th.
Yes.
I don't remember if you said it or not. Is the final cumulative or is it just
Um,
this section?
I think I said it would not be intentionally cumulative.
But there, so would
So
there be
what that
questions?
means, well, what that means is you still need to know the notation of set because the algorithms use
Oh, well,
set
yeah,
notation.
but there's not gonna be anything like specifically on like relations or like.
That is correct.
Okay.
So it's not going to be intentionally cumulative,
Okay.
but it can still be cumulative from the sense of the new material.
Yeah, you have to
Some of those
past
are
acquired
expressed
knowledge, yeah.
using terms that we discussed in the past.
All right. Cool.
Yep.
Thank you.
Mhm. So you need
This is that no problem. What you do?
no problem.
Exam for me as this TS student.
Right.
All time
So you-
same problem. Maybe need.
So you need to fill in a form first. Okay, that is for you to fill in. Go to the DSPS website, and there's a form for you to fill in.
Okay.
And then once I have the cover sheet, I can then send the DSPS test center the actual test. Now, if they leave, and they're going to be done by 4 p.m., we have a problem. But I can make your exam start earlier, so we don't have that problem. So I would say, go to that website now or as soon as possible. Find that link, find that form that you need to fill in, and then send me the cover sheet that you have created. Is that okay?
Okay.
All right.
Next, still at the bottom, and then also the links that you sent out are swapped.
The links. Yes, I know.
Okay, yeah.
Yep.
I just missed that part. Yes.
Yep.
If you're gonna uploading the like older than spring 2022 final exams for like more practice, like for if we upload like
You
fall
want an
20
earlier one?
yeah, like a fall 2021 final or something.
That one is a little bit more involved. It's a little bit too hard for for this class. Send me an email. I'll reply with the test.
Okay.
Yep.
Thank you.
Yep. Because the exam of spring is a little bit easier compared to the fall of 2021. Yep. Yeah. But if you send me an email, I will send that to you too.
Thank you.
Mm-hmm.